The complex wave then. Here is an example of a complex wave. Complex in the sense that it's a wave, so it's got like a period, so it's periodic here, and then the same here. So the wave is the same, supposed to be anyway according to my sketch, here as here as here, and it's got a period. It's complex in the sense that we can think of it as being made up of one sort of wave, a fundamental, which, and if you think back to the ideas on the fundamentals and harmonics, this is the fundamental frequency with half a wavelength, so we can imagine this carrying on, half a wavelength in the period that we're interested in. But also we could fit harmonics on here, which are waves that do this in the same interval, or a third harmonic, which would be 3 half wavelengths. So we have the fundamental, which is this first one, and then the harmonics. We can think of a complex wave like this one here that's being made up of a fundamental, which looks as though it's got a frequency of roughly this, but also harmonics on top, which might have higher frequencies, which are multiples of half wavelengths of the fundamental. So the frequency of the fundamental would be a given value, the first harmonic would be exactly twice that frequency, the next harmonic three times, the third harmonic 3 times the frequency, and so on. And you can almost see we've got harmonics here, look, these frequencies look to be higher than the fundamental frequency, which is this one. So that idea, combined with the idea of superposition, which is that if I have a wave like this, coming this direction, say, so let's draw it out, and then another wave, say with a different amplitude and different frequency, coming this way, what will happen is, when they meet, we'll have some sort of complex wave made up of those two. And then afterwards, they'll carry on, so this wave will carry on over here, and this wave will carry on over here, unaffected. But at the point where they meet, which is this point here, I can think of this complex wave being made up of these 2 or even 3 waves all adding together to give this complex wave. So the idea of the Fourier series is to break down this complex wave here into a fundamental and harmonics. So that gives us our Fourier series, which is here. So here is our complex wave, some function, and we're going to break it down to some constant, which will turn out to be some sort of DC offset or something if you think of it in electronic circuits, plus waves, other waves, simple waves. And if you look at them, you can see for a start off we've got a series of cosine waves and sine waves. Think back to the Fourier series that we were talking about before, where we could break down a function into a power series with terms involving x, x squared, x cubed and so on, all possibilities. Here we're containing all possibilities. My complex wave could be made up of this constant, then a series of cosine waves, and a series of sine waves. It might or might not have all these waves in it, but we allow for the possibility. Notice that this is the first harmonic or fundamental, and then the second harmonic where the frequency, i.e. the angular velocity, is twice that of the fundamental, 3 times, and so on. Same for the sine, there's the fundamental, second harmonic rather, third harmonic, and so on. So we've got all these waves, all these harmonics that could add up to make this complex wave which we've got here. For this Fourier series to work, it must be periodic. That's the most important thing. So we're assuming that the wave we're trying to describe is periodic. In other words, it looks the same over here. If we find out what the wave looks like for this period here, then it's exactly the same for this period here, and so on. And there are other things that must be true, and they're outlined here. So if we look at them, the constant term at the start appears if the function does not have a 0/1 cycle, i.e. there's some sort of DC overlay. We define A and B, A1, B1, A2, B2 and so on as the Fourier coefficients. Something we need to talk about in a minute, and the next video will be even and odd functions. As it turns out, if the function is even, then there are only terms involving the cosine, which means that we can ignore all the sine harmonics. And similarly, if the function is odd, then there are only terms involving the sine, so we can ignore all these cosine terms. So that immediately halves the work we've got to do to come up with the function. Just to restate, the terms involving A1 and B1 and so on are called the first harmonics, and then the second, third, fourth harmonics. So I'll stop this here and then we'll carry on to the next video clip.